Hello, I welcome you all to your own channel MSK Learning. In this video, we will discuss one truss problem which is related to the finite element methods. So the problem on the screen, for a 2-bar truss shown in the figure, determine the nodal displacement, element stresses. The load is given that P is equal to 1000 kilonewton is applied at node 1. Assume the Young's modulus is 200 GPa, means gigapascal, and the area is 600 mm square for each element. So the figure is here. You can see the two element truss is given. That is, this is the element 1 and this is the element 2. Here you have a node 1, the node 2 and node 3. Right? The load is acting towards left direction, horizontal at node 1, whose magnitude is given 1000 kilonewton. The Young's modulus for each member, that is for each element, is 210 GPa we have to take, and the area of each member, that is the area of this member and area of this member, is 600 mm square. We have to find out the nodal displacement at node 1, node 2 and node 3, as well as we have to find out the stress in element 1 and the stress in element 2. So as you know that this is the truss problem, so in truss at each node the nodal displacement will be on x-axis as well as on y-axis. It means that in this node, at this node 1, the nodal displacement will be on x-axis and on y-axis. Similarly at node 2, x and y. Similarly at node 3, x and y. So how many total nodal displacement for this element? As the node are 3, so 3 into 2 means 6 nodal displacement will takes place. Similarly, on each node, the forces will act on x-axis as well as on y-axis. But if you remember, for one-dimensional bar element problem, the force and nodal displacement at each node on only one axis, that is either on x or on y. Right? But in this case, the nodal displacement and force at each nodes will be on x as well as on y. So first of all, we'll do for the calculation, means for element 1. So we'll start, and before that we can write down the given data, that solution, that given you have a load is 1000 kilonewton, right, at node 1. So it is left, so it will be minus, I'll take minus 1000 into 10 to the power of 3 Newton, right. Area of each member, that is A1 is equal to A2 is equal to 600 mm square, right. Young's modulus for each member, that is E1 is equal to E2 is equal to 210 GPa, gigapascal. So our calculation is in millimeter, so it will be 210 into 10 to the power of 3 Newton per mm square, right. Now we'll take individual for each element, element 1 and element 2. So first of all, we'll begin with the element 1, right. So you can write a step 1, a step 2 also, right. First we'll go for the element 1. For element 1, this is the model element 1, right. So how the element 1 is there, you can look at the figure again. Element 1 is this, right. So we will take this element and we are keeping this element into xy plane, right. So now here I'll take, that is, this is your element 1 is kept like this, is it or not, right. So if you look at, that is from this to this, it is 4 meter and this is 3 meter. So for convenient, if I say that this body is in this, like this, it is in the plane xy, right, it is in the plane xy. Now you can understand easily, that is, this is your y-axis and this is the x-axis, is it or not. So it means that this is the origin, this is the node 1 and this is the node 2, right. So the coordinate at this point is what? The coordinate at origin will be 0 0, right, and the coordinate at here, that is 4 meter, means we'll take in the millimeter, so it is 4000 and y is 0. Again at this point the x coordinate will be 0 and y coordinate is 3 meter, means plus 3000. Got it? So this means what you can say. So for element 1, right, for element 1 you have a, this is the node 1, right, and this is the node 2. At node 1 you have a nodal displacement, you can say the two nodal displacement, let's say this is the, on x-axis it is q1 and on y-axis it is q2, right, and at this node 2 on x-axis the nodal displacement will be q3 and on y that is q4. Okay, similarly the load at this node 1 F1 and F2 F3 and F4, right? First of all, we need to find out the length of this element, right? So we will find the length of the element, length of element, similar length of element. Let's say it is LE. So LE is equal to what? LE is equal to root over of x2 minus x1 whole square plus y2 minus y1 whole square, right? What is the x2, x1? See, that is for node 1. This is the x1, y1, and for this it is the x2, right, and y2, right? And when we take this as a element, it is x1, y1, and this is x2, y2. Is it or not? For element 1, this is the condition, that is x1, y1, x2, y2, and this is the x1, y1, and this is the x2, y2, right? So first you have a x2, y1, x2 minus x1 means x2 is 0 minus 4000 whole square plus 3000 minus 0 whole square. So it is 5000, right? So LE is equal to 5000 millimeter. Length of the element 1 we calculated. Now we'll find out the direction cosine, that is cos and sine. So direction cosine, right? Direction cosine. So direction cosine is what? That is cos theta. Cos theta we denoted by L is equal to x2 minus x1 by LE, right? So x2 minus x1 is what? That same 0 minus 4000 by 5000 is equal to what? Minus 0.8. Okay, then another direction cosine, that is sine theta, is equal to m is equal to y2 minus y1 by LE, right? So this is what? Y2 is 3000 minus 0 by 5000, so it is 0.6, right? Now we will say the stiffness matrix, right? So K we have to find for element 1. So we'll go next. So first of all, we will find out the K1, right? That is stiffness matrix. Just wait. Yes. So stiffness matrix. Stiffness matrix. That is K1. For truss, the stiffness matrix formula is what? K is equal to A1 E1 by L1 L square Lm minus L square minus Lm Lm M square minus Lm minus M square, right? Then third we have minus L square minus Lm L square Lm Lm minus M square, right? Lm, and again you have a M square. This is minus, right? So this is what you have a stiffness matrix for element 1, right? Now similarly means need not to be worried about that. That is L square Lm minus L square minus Lm Lm M square minus Lm minus M square, and then these two term will come into the third row, and this two term will here, right? And again this two term will be come in fourth position, and these two will be here. So just you have to replace, right? Then we will substitute the values. That is K1 is equal to, area is what? Area is 600. E1 is equal to 210 into 10 to the power of 3 by length of the element 1, that is LE we have calculated, which is 5000, right? So L square is what? L is equal to, you can see that for element 1 L we calculated minus 0.48, and this is the M is 0.6. So L square will be the 0.64, right? So it is 0.64. This is 0.8 into 0.6 means minus 0.48, and this is the minus 0.64. Actually it is minus. So minus will become plus, and because of this minus it will come in the terms of minus only. So again it will become plus, that is 0.48, right? The second is Lm, means same minus 0.48. M square, that is 0.36 minus Lm means it is 0.48 plus minus will become plus and this is minus 0.36. Now you have to replace that. These two terms will come here and this will be here, right? So similarly we can substitute minus 0.64, 0.48, and this is 0.64 and minus 0.48. all right, then these two terms will come here, that is 0.48 minus 0.36 minus 0.48 and 0.36. This is your K1, that is element 1. But this simplification we have to do. What we will do actually, we will take 10 to the power 3 common and then multiply this. So when you simplify this whole term, you will get the values as a 25.2 into 10 to the power of 3. Right? This is the whole calculation is there. So for understanding purpose I am writing here, but while you do the problem, you can understand what is the value. So this value you have to multiply with these terms, right? Now, so on simplification, further this stiffness matrix K1 will become like this. In this 25.2, I'll multiply with the whole values, and 10 to the power 3 I'll take it out, right? So 10 to the power 3 I'm taking common. So this is your matrix will become like this: 16.128, right? Minus 12.096 minus 16.128, 12.096 minus 12.096, 9.072, 12.096, 9.072 minus 16.128, 12.096, 16.128 minus 12.096, then 12.096 minus 9.072 minus 12.096, 9.072, right? So this is what you got the K1 for element 1. Now we'll go for the element 2. So before that, element 2, we'll see the how the element 2 is look like, right? So this is your element 2. Is it or not? Which is connected between node 1 and node 3. So the coordinate at this point at 4000, 0 and the 0, 0. First we'll calculate the length and then we'll calculate direction cosine, that is L and M, and then we'll find out the stiffness, right? So first we can say, next we have a element 2, right? So first of all we will see that for element 2, right? For element 2, how the element 2 is this? It is like this, is it or not? That is node 1 and this is the node 3, right? Here you have a that is nodal displacement will be the Q1 and Q2, and this is what you have a Q3, Q4 is for element 1. So this is what you have a Q5 and Q6. Similarly F1, F2, F5, F6, is it or not? The coordinate is here, which is the 4000, 0, right? And its coordinate is 0, 0. Why? Because it is at origin, right? So again I'll show you. This is what you have a 4000, 0 and 0, 0. Here you have a nodal displacement is Q1, Q2, and this is the Q3, Q4. This is Q5, Q6. So that's why it is Q1, Q2 and Q5, Q6, right? Now, so first of all we will find out the element, that is length of the element, right? So directly I'll say LE is equal to what? LE is equal to x2 minus x1 whole square plus y2 minus y1 whole square. X2 is this one, that means 0 minus 4000 whole square plus 0 minus 0 whole square, right? So you can say 0 minus 4000 whole square plus 0 minus 0 whole square. All right, so it is what? 4000. LE we got. Then we'll find out the direction cosine, that is cos theta. Cos theta is equal to what? L, that is x2 minus x1. 0 minus 4000 by 4000, right? It is equal to minus 1, right? Then we'll find out the sine theta, that is M. So we will find out the sine theta is equal to M, which is y2 minus y1 by LE, means 0 minus 0 by 4000. So this is the 0. Then we will find out the stiffness matrix, which is K. So next we can find So now we have to find out the stiffness matrix K2, right? So similarly you have a element stiffness matrix K2, right? So K2 is equal to what? A2 E2 by L2 LE L square LM minus L square minus LM, right? LM M square minus LM minus M square. That's so. First of all, area is what? Area is equal to same 600. Young's modulus is 210 into 10 to the power of 3, and LE we calculated, which is 4000, right? Then we have a, sorry, we did not find out the, yes, we calculated the LM right now. So you can see here, I'll show you, that is for element 2, that is the LE is 4000 and the direction cosine cos theta is -1 and M is 0. Wherever the M and LM is there, that term will be 0, and wherever the only L is there, there is a 1 value will come. Is it or not? Why? Because M is 0. So that's why this is the, you have a 1, L square is 1, that is -1 whole square is +1, right? LM means it will be 0. Again minus L square means -1, and this is 0. In second row, all values are in terms of the M. So it is 0, 0, 0 and 0. In third row, that is, this is minus L square, that is -1, L minus LM 0, L square 1, and this is 0. In fourth also it is 0, 0, 0, 0. So this is what you got. Then on simplification, you have to simplify this term and then multiply with these values, right? So on simplification, we'll get this value as a 31.5 into 10 to the power of 3. So we'll take 10 to the power 3 as a common. Why? Because we have taken 10 to the power 3 common in K1 also, right? So here you have a 10 to the power 3, and this 31.5 will multiply with these rest of the values. So it will become 31.50 minus 31.5, 0, 0, 0, 0, 0, right? Minus 31.5, 0, 31.5, 0, 0, 0, 0, 0, right? Then stiffness matrix K2 we calculated. Now what we need to find means we have to club them, means globalize them, right? So first of all, we will find out the global stiffness matrix, that is K is equal to K1 plus K2. So here we go, that is global stiffness matrix, right? Global stiffness matrix. So what is the global stiffness matrix? That K is equal to K1 plus K2. So again you can look at the question, that how many nodal displacement we are getting. That is, here you have a, at node 1 you have a nodal displacement is what? That is Q1, Q2. At node 2 the nodal displacement is Q3 and Q4, and at node 3 that is nodal displacement is Q5 and Q6. As it is the Truss problem, so at each nodes we have a 2 nodal displacement. One is on x-axis and one is on the y-axis, x and y, right? So the 3 nodes is there, so total nodal displacement is what? 6. So the final matrix, that is size of the matrix after addition, it will be 6:6, right? Okay, if the node is 4, then the size of the matrix will be 8. If the node is 2, the size of the matrix will be 4, right? Just twice. So here we will find out the K, that is K1 plus K2 you have to add. So how you add, you know, that is, first of all I will write, that is, just wait, that means K is equal to 10 to the power of 3, as we have taken common everywhere, right? So here I'll show you, right? This is the Q1, row 1, Q2, Q3, Q4, Q5, okay, and this is the Q6, right? Similarly, we don't have a space here, or you can write here only Q1, Q2, Q3, this is for column, Q4, Q5 and Q6, right? So we will take the values from each element, that is the stiffness matrix we have calculated K1 and K2, right? So your K1 is what? This is what? The K1 is, you can see it is connected between Q1, Q2, Q3 and Q4. This is Q1, Q2, Q3 and Q4, right? Similarly, this element 2, that is for element 2, stiffness is connected between which two nodes? That is Q1, Q2 and Q5, Q6. Q1, Q2, Q5 and Q6, right? So you have to simply, you need to take the values from, you have to check what is the Q11. Q11 is 16.128, right, from the element 1. So 16.128, right? Q22, Q12 is what? Minus 12.096. So minus 12.096, right? Similarly, Q31, that is minus 16.128. This is 12.096. 31.5 minus, this is 0, right? And again we have a minus 12.096. This addition we already did in the previous chapter. Right now means previous problem, you can go through with this. 9.072, 12.096, 9.072, 0, 0, right? 16.128, 12.096, 16.128 minus 12.096, 0, 0, right? Then there was fourth, 12.096 minus 9.072 minus 12.096, 9.072, 0, 0. Fifth, we have a minus 31.5, 0, 0, 0, 31.5 and 0. And the sixth one, we don't have anything, 0, 0, 0, 0, right? So this is how you added the matrix Q, K we got. Now we have to formalize the finite element equation, right? So you can see here that finite element equation, finite element equation, right? So what is the finite element equation? That KQ is equal to F. KQ is equal to F, right? So KQ is equal to F means what? It's global stiffness, global nodal displacement and load vector. So again we will write down K here, that is 10 to the power of 3. So this is your 16.128 minus 12.096 minus 16.128, 12.096 minus 31.5, 0, minus 12.096, 9.072, 12.096, 9.072, 0, 0, 16.128, 12.096, 16.128 minus 12.096, 0, 0, right? Then 12.096 minus 9.072 minus 12.096, 9.072, 0, 0. Then minus 31.5, 0, 0, 0, 31.5, 0, 0, 0, 0, 0, 0, 0, right? This is the K. Beside that you have to write Q. That is Q is equal to what? Q1, Q2, Q3, Q4, Q5 and Q6, right? Is equal to F. So F is equal to what? F is equal to, you have a F1, F2, F3, F4, F5, F6. So here you can look at, this is what? F1 on x axis, F2 on y, F3 on x, F4 was y, F5 on x, F6 on y, right? So at 3 nodes, at each nodes you have a 2 forces, means one is x axis and one is on the y axis. But if you look at that force on x, means on horizontal direction towards left, is given P, and P value is given 1000 kilonewton, right? So this value is given, but at the rest of the point we don't have any force. Even at node 1 the vertical force is not given, so F2 will be 0, F3, F4 will be 0, F5, F6 is 0. Why? Because it is not given. Only the force on x axis it is given towards left and its value is given. That's why we will take F1, and the rest of the value will be 0, right? So this value is minus 1000 into 10 to the power of 3. Why? Because minus 1000 into 10 to the power of 3, minus is P is acting on the node 1 left direction horizontal, so that's why we are taking minus, and the rest of the forces is not given. It is 0, 0, 0, Q5, F6 is 0. Now we can solve this problem by using elimination approach. So what is the elimination approach? First of all, we have to impose the boundary condition. So the boundary condition is boundary condition, right? So what is the boundary condition? Look, let's see that again. That this is the problem, right? If you look at the node 1 is the roller support is given. Roller support means when the load is act on the truss member, it can move on horizontal, but the vertical it cannot move. Why? Because it is hinged, right? At this node 2 and node 3 it is hinged, so neither it can move on x-axis and nor it can move on y-axis. So at this node and at this node, all the horizontal and vertical nodal displacement is 0, and at this node the vertical displacement will be 0 and the horizontal displacement is having some value. Why? Because roller is there, right? Now, so you can see that Q1 is Q2 is equal to Q3 is equal to Q4 is equal to Q5 is equal to Q6 is what? 0. Except Q1, all are 0. Why? Because the 1 is having value. Why? Because it is roller support, right? So as it is roller, so when the load is at, it can slide, means it can move, right? So that nodal displacement we can find at the node 1 on x-axis, but on node 1 at y-axis we have a 0. Why? Because it is hinged. And at node 2 and node 3 is completely hinged, so neither on x-axis nor on y-axis it will be 0, right? It will be 0 only, right? So when we impose the boundary condition, it means that except first row and first column, all the element will be eliminated, right? So we can impose the boundary condition here only. So this is how you can eliminate that. First we are eliminating the Q2, means this is the Q2, right? And second row, second column, again you have a third row, third column, right? Fourth row, fourth column, right? Fifth row, fifth column, sixth row and sixth column. So this element we have not eliminated. Why? Why? Because at this point we are getting Q1 is having some value, right? So all are eliminated. The matrix is reduced into 1:1 size. So now you can simplify. Just wait. So the after elimination, the matrix is become 10 to the power of 3 is there, and that is the 16 point. Sorry, it is not 16. That is 47.128. Right. This is the make a correction. That is 47.628. Right. So it is 47.628. 47.628. Right, and this is what you have a Q1 is equal to minus 1000 into 10 to the power of 3. So when you simplify, you will get the Q1 value. Q1 value is you have a 20.996 mm, right? It will come in minus, right? So the nodal displacement is what? Your answer will be like this, that nodal displacement that Q is equal to Q1, Q2, Q3, Q4, Q5, Q6. So Q1 is what? Minus 20.996 and Q2 is 0, Q3 is 0, Q4 0, Q5 0 and Q6 0. We have a transpose. This is the first answer. Then we have to find out the stresses in each member, right? So there is a formula for finding the stress in each member in a truss, right? So now here we can find that stresses in each member, right? In each member. So for element 1 we can find first for element 1, right? So how? That is sigma 1 stresses in member for truss member is formula is E by LE minus L minus M L M, right? And the nodal displacement. So element 1 is connected between which two nodes? That is 1 and 2, and the nodal displacement is Q1, Q2, Q3, Q4. So beside that we will write that is Q1, Q2, Q3 and Q4. This is the formula for finding the stress in truss member, right? So Young's modulus is given for the element 1. It is 210 into 10 to the power of 3, right? By LE we have calculated, which is 5,000, right? That is 5,000, and minus L is what? That is 0.8. Let me check. Yes, so minus 0.8 means it is plus 0.8. Minus M means 0.6, so it is minus 0.6. This is minus 0.8 and this is 0.6, right? Q1 value we calculated minus 20.996. This is 0, Q2, Q3 and Q4 is 0, right? So you can simplify that. How? Let me check. That is, this is 210 into 10 to the power of 3 by 5,000, right? And this value will be multiplied this into this, that is 0.8 into 20 minus 20.996 plus minus 0.6 into 0 plus minus 0.8 into 0 plus 0.6 into 0, right? So this is how, means this 0.8 into this plus this into this plus this into this, right, plus this into this. So on simplification you can simplify and you'll get the value, which is minus 705.47 Newton per mm square. This is the sigma 1 stresses in element 1 we calculated. Similarly, a stress in member 2 we can find, that is a stress in element 2, right? Stress in element 2. So stress in element 2 is what? Sigma 2 is equal to E by L minus M, L M, Q1, Q2, Q5, Q6. So I'll write here, that is E by L, E, right, minus L, minus M, L, M. Is it or not? Then that element 2 is connected between 1 and 3. So 1 is what? That is Q1, Q2 and Q5 and Q6. Okay, then E is equal to what? 210 into 10 to the power of 3 by LE is 4,000. This is for element 2. L is equal to, for element 2 L is equal to minus 1, so it will be 1, right? And M is 0, so it is 0, and this is minus 1, right? And this is 0. So Q1 is what? Again you have a Q1 is minus 20.996. This is Q2 0, Q5 0 and Q6 0. So you can simplify that this is 210 into 10 to the power of 3 by 4,000, right? And 1 into 20. So this is 1 into minus 20.996 plus 0 into 0 plus minus 1 into 0, right? This is minus 1 into this 0 plus 0 into 0, right? So simplification, you'll get the sigma 2 is equal to 1100.7 Newton per mm square. So this is how we will solve the truss problem, right? So these all are the method by which you can find out the stiffness, nodal displacement and the truss in a stresses in a truss member. Thank you.